And so the diffusion that happens within here, you treat very differently from the diffusion that's happening in a bulk. Yeah?
Now, if the diameter is on the order of angstroms, then how could you get anything larger than the hydrogen into it?
So, I mean multiple angstroms. I don't mean a single angstrom. But you would characterize it as, for example, zeolites. I think we've mentioned those previously in the class. They have micropores, they have molecular size pores, essentially. So for example, some molecules can fit in, but other molecules cannot. So if the molecule is too big, that is why people use zeolites. That's one of the main reasons why people do, is because some molecules cannot fit into the zeolite in order to react. So it gives you reagent selectivity properties based on size exclusion. It also gives you transition state selectivity properties, because once I'm in, I can, for example, make paraxylene, but not orthoxylene or metaxylene, because those are a little bit larger because of their shape. One of them, it looks like this. So which one is that? And this one is harder to fit if I have a very tight pore. And so I can actually do this type of chemistry where I make xylenes, but only of a selective type. And then on the same token, you have product selectivities, because some things you make inside the zeolite, but they get trapped there. They can never leave. And it actually leads to catalyst deactivation, because you made something too big that can never escape. So no, it's a good point. And so that also tells you that diffusion within those properties is going to be very different, right? It's like single file diffusion. You can't pass the guy in front of you. So it's definitely not the same as bulk diffusion. And this is actually what Sergey's group, Visenkov's group studies research-wise, is they look at diffusion within very small regimes like zeolites. So out here you have external diffusion, this region right here. External diffusion, meaning outside the support particles or just the catalyst particles. And then you have internal diffusion. And again, those are going to behave very differently because of the different length scales involved. What about on the surface? Can we have diffusion there? If something sticks to the surface, does it stay in one place or can it move around? It can also move around. So you can also have surface diffusion. These are two-dimensional surfaces. And sometimes those surface diffusion rates actually matter. So in all these cases, external diffusion, internal diffusion, and surface diffusion, they can all impact the measured rate of the reaction, even though they have nothing to do with A star goes to B star. So these are typically referred to as mass transport limitations. And these mass transport limitations are one of the things that we'll talk about in this third section. And then, of course, once we're on the surface, you have adsorption, surface reactions as well, and desorption, which is just the opposite of adsorption. So notice only one of these processes in this huge list is a chemical reaction. And yet all of these processes can, in some circumstances, limit the rate of the reaction and therefore affect what is it when we measure a rate. That's always a question that we have to figure out when we're doing catalysis, is what are we measuring when we measure a rate? So the first thing we're going to talk about is adsorption. We're going to come back to and just briefly talk about how we deal with the external and internal diffusion. External diffusion is usually not a big deal. Internal diffusion can be very important, and we'll talk about how we can do experimental tests to figure out if we're diffusion limited, and how we can set up some equations to figure out if we're diffusion limited. The first thing we're going to talk about is adsorption, which again is the reverse of desorption. So talking about one is like talking about the other. there's two main types of adsorption that we have to concern ourselves with. One is physisorption. And what's the other one? What are the differences between those two? Okay. Good identifying the root word. Care to elaborate?
Chemisorption is a substance actually bound to the surface, whereas physisorption is just kind of stationary.
All right, so let's take a couple of molecules as examples. So methane. Can methane bind to a surface? And if it can, by what chemical mechanism can it bind? Yeah, let's not, we're talking about methane. If it loses a hydrogen, it has a totally, it's not methane, right?
Van der Waals?
But it can't form a chemical bond through van der Waals. And so that's what happens. You can interact with a surface. Methane can interact above a metal. Move this. Above some metal, and it can interact, and the way that it interacts are through van der Waals type of interactions. So what are van der Waals interactions? Hydrogen's involved in van der Waals interactions, but I don't need to have any hydrogen to have a van der Waals interaction. Temporary dipoles, right. They're induced dipoles. So methane does not have a dipole moment, right? Each bond has a dipole, but they're symmetric. So the overall dipole moment's 0. But because those bonds have dipoles, when the atoms vibrate, they can be vibrating in such a way that reduces the symmetry of the molecule. So at 0 Kelvin, there's no dipole moment, but at temperature there is. And that can also induce dipole moments in a metal surface, which can already have a dipole moment in themselves. But these dipole-dipole interactions can be attractive. And these are often referred to as van der Waals. I'll write it out. Interaction. What other type of interactions what might there be? If I keep pushing the methane closer and closer to the surface, will it ever feel repulsion with the surface? And through what mechanism? What's the other chemical mechanism that we would invoke? It's related to electrons. So polyrepulsion is essentially saying that electrons don't like to be in the same space. So I can't push two atoms very close together unless there's something to overcome that, like a chemical bond that's formed. Dipole-dipole interactions will get them somewhat close, but not that close. And so the other thing that we can do is we can measure or calculate an energy associated with that adsorption process. And this energy is typically for a physisorption on the order of, we'll say, negative 20 kilojoules per mole.
How is it measured by kinetics? Or?
You can infer it from kinetics, but only in certain ways. But yes, you can infer it from kinetics. And we'll talk about that once we develop a greater understanding of catalysts, of solid phase kinetics. We'll talk about how you can measure the adsorption energy. The other way that you can do it with measurements is through calorimetry. So calorimetry is a way of getting a very precise measurement of how much temperature changes in a closed system. And so you create a closed system, you put in a very nice thermocouple, and you expose a metal to methane, and you see how much heat is released. Now, of course, you have to do it at conditions where the methane won't react, because then you're measuring the heat released from adsorption, but also the heat released from the reaction. Yeah?
This is kind of a, it might be an option, it might not, but like, you know how in physics when they're trying to, for the Van der Waals equation, how there's like a repulsion part and an attraction part, and they try to measure it by polarizing molecules?
Yeah.
Is this kind of the same idea?
Yeah, I mean, that you can, so like a Lennard-Jones potential is what you're thinking of, this shape, where it's very steep, and then it comes down to a minimum, and then it comes out like this. So, I mean, this type of potential can describe Van der Waals interactions. It can also describe chemisorb species. But yes, it can also be used for physisorb species, where this is where the methane wants to be relative to the surface. So this scale is like the distance between the methane and the metal. And if I move it out too far, at some point it stops interacting, and if I push it too close, it gets very unhappy. But that shape is also can be used to describe the CH bond length within methane as well. So it's not just Van der Waals interactions. That shape is useful for a lot of different types of interactions. What else is here? Yeah, so let's talk about some other things about physisorption. Do we think that the surface matters a great deal? Does the chemical ability of the surface matter during physisorption? It doesn't have to form chemical bonds. So this surface can not just be the metal, which is active, but it could also be an inactive species as well.
Or physisorption benefited by having a more polar surface there?
Yeah, when you get into that level of detail, yes. But the point is that you can physisorb something on an inert surface. You cannot, sort of by definition, chemisorb something on an inert surface.